Hello and welcome to the channel. Today I'm going to work through problem 3.7 out of Griffiths' Introduction to Quantum Mechanics. Before I get through actually solving this problem, I'd just like to ask, if you're not already, please subscribe to my channel and like the video down below. It's a great way to support me. It's free, it helps me, and when you do that I'll post more videos that have solutions from popular undergraduate physics textbooks like this. So if you're a physics student or if you're just interested in physics, I think you would enjoy my channel. Now let's get into actually solving this. Part A. Suppose that f of x and g of x are two eigenfunctions of an operator q with the same eigenvalue, little q. Show that any linear combination of f and g is itself an eigenfunction of the operator q with the eigenvalue q. So what this is saying is that if we let the operator q act on f, you get an eigenvalue times f. That's what it means, that those are eigenfunctions of the operator q. And we can say the same thing with g. And they're both equal to q because it's stated so in the problem. So let's consider q acting on this linear combination of f plus g. In fact, to show that any linear combination would work, let's rewrite this as c1f plus c2g. So this is just some linear combination of f and g, where c1 and c2 are constants. Well, this is equal to q operating on c1f plus q operating on c2g. Now, the constants, since those are constants, those can be moved out front. I think this is pretty straightforward so far. And we know what these are equal to by what's given in the problem. So we have c1 qf plus c2 qg. Okay, well, we can factor out this common q because they both have this q term, and you're left with c1f plus c2g. But that is a linear combination because we started with this, where this is an eigenequation. So we're saying that q operating on this linear combination of known eigenfunctions is just equal to some constant q times that same linear combination. So that essentially proves what we're trying to show, that it is an eigenfunction. B, check that f of x equals e to the x and g of x equals e to the minus x are eigenfunctions of the operator d squared dx squared with the same eigenvalue. Construct two linear combinations of f and g that are orthogonal on the interval -1 to 1. Okay, so we have this operator acting on, we'll start with e to the x. And just so you're okay with this, this is the exact same thing as just taking the derivative twice. Now, when I take the derivative of e to the x, that's going to be just e to the x. And then the derivative of x with respect, the derivative of x of e to the x is still e to the x. So this whole thing is just e to the x. And in this case, so we're operating, we have something like this. Q hat e to the x equals 1 e to the x. And in this case, Q hat is just this operator. So clearly this is an eigenfunction. We get our function back, and the eigenvalue is just 1. Now we can try the exact same thing with e to the minus x. You might find it helpful to just rewrite this operator like this. I always find it helpful myself. Well, this is a pretty easy derivative. This is minus e to the minus x. And then when we take the derivative of that, the negative sign will go away, and it's just e to the minus x. So this is equal to 1 times e to the minus x. So we have q hat operating on e to the minus x. It's equal to 1 times e to the minus x. So sure enough, this is an eigenfunction, and we have the same eigenvalue, which was promised in the problem. Now, we want to construct two linear combinations of f and g that are orthogonal eigenfunctions on the interval -1 to 1. So again, f equals e to the x. This is f of x. And g of x is e to the minus x. So the first two that come to my mind are whenever you have exponentials like this, and they're not complex, there's no I. If there was an I in the exponent here, I would consider using Pythagorean's identity, or Euler's identity, I'm sorry. But since there's not, we can define our hyperbolic sine and cosine using these exponentials. So if you're not familiar, I think I have a video going through some problems that are related to this in chapter 2. This is the definition of sinh of x. And very similarly, only difference is there's a plus here. This is the definition of cos of x. And these are surely a linear combination, right? We're adding and subtracting them, and then we're just multiplying them by the same factor of 1/2. And those are definitely orthogonal on that interval. You could work it out like this. Oops. And you'll have a 1/4 because there's a 1/2 attached to both sides. So if you were to distribute this out, you'll get an e to the 2x this is 1, but then that is minus 1, so that's just going to be 0, and then plus e to the minus 2x dx. So just really quickly to show you, we're going to have 1/2 e to the 2x evaluated on this interval plus, oops, this should have been a minus sign. There we go. E to the minus 2x evaluated, so the negative sign will turn positive. And this is just going to be 1/4 times 1/2 e to the 2 minus 1/2 e to the minus 2 plus 1/2 e to the minus 2 minus 1/2 e to the second power. And clearly those cancel and you get 0. And not only that, we know that this is also an eigenfunction because we just proved that a linear combination of two eigenfunctions is itself an eigenfunction. So hopefully that helped, and if it did, please like the video and subscribe.